Okay, guys, so now we start the next chapter, and next chapter, that is the continuous probability distribution. Some continuous probability distribution. Now, guys, please look at here. One of the most simplest continuous distribution in all the statistics, that is the continuous uniform distribution, because that's just give the rectangle, and sometimes it is known as the rectangle distribution too, because it is defined between the closed interval a to b. And flat, why flat? Means it gives you the rectangle because it's just one line, your fx value, function value. So one of the simplest continuous distribution in all the statistics is the continuous uniform distribution. This distribution is characterized by density function. Density function is, if whenever you find this word density function, it is always to be understood that we are talking about the continuous distribution, because it's nothing but the integration. And that is flat, and thus the probability is uniform in the closed interval. Probability is just uniform in the closed interval, a to b, closed interval a to b. If you take open interval, even though we are going to take the integration between that lower range to upper range from initial point to final point, and that's why it is just the integration. And the density function of the continuous uniform random variable x of the interval a to b, that is given by f of x a b equal to 1 over b minus a, where x lies between capital A and capital B. Otherwise, it is 0. What does it mean? That means, suppose I have something like this. Look at over here, that between 1, 2, 3, whether it's open or closed interval 1, 2, density function 1, 2, 3. Now my a equal to 1, b equal to 3, and my fx is nothing but 1 over b minus a. So 1 over 3 minus 1, that is equal to 2. So 1 by 2 is my fx. So that is 1 by 2, and that's why that is called the flat. And you can see over here, because of this flatness, you're going to get the rectangle. And that's why this uniform distribution is also known as the rectangle distribution too. Okay, rectangle distribution too. And that's why it is mentioned over here. Look at here, the simplest distribution. Anyway, so the density function here forms a rectangle with base b minus a, that is my base b minus a, and the constant height of 1 over b minus a, as I showed you here. B minus a, that is my base, and constant height of 1 over b minus a, that is my constant height. Okay. As a result, the uniform distribution is often called the rectangular distribution too. Doesn't matter if you take closed interval or open interval, because density function for a uniform random variable between 1 to 3, or it is open interval, we are going to count those numbers. You know this thing. So, however, note that the application of this distribution is based on the assumptions that the probability of falling in an interval of fixed length a to b is constant. Probability of falling in a fixed length of a to b, that probability is just constant. So whenever we have this type of things, that is called the uniform distribution. Let's go for this example. This example says that suppose that the large conference room at a certain company can be, okay, suppose that a large conference room at a certain company can be reserved for no more than 4 hours. No more than 4 hours means at the most 4 hours, 2 hours, 3 hours, 4 hours, 1 hour, something like that. Both long and short conferences occur quite often. In fact, it can be assumed that the length x, that is a random variable, length x of a conference has a uniform distribution on the interval 0 to 4. On the interval 0 to 4. The question is, what is the probability of that density function? Now you can see over here in this density function, my length is 0 to 4, right? Interval is 0, means a, capital A equal to 0, capital B equal to 4. So capital B minus a, that is equal to 4 minus 0, that is equal to 4. So 1 over 4. So my function f x a b, now that is equal to 1 by 4. That is equal to 1 by 4. Right, guys? And x lies between a to b, that is equal to 0 to 4. What is the probability that the given function, what is the probability that any given conference at least 3 hours? At least 3 hours means 3 and more than 3. So x greater than or equal to 3, that means my integration is 3 to 4, and fx dx. Fx is 1 over 4 dx, right? By definition, 3 over 4 and 3 over 4 and fx dx. So 3 to 4 and 1 over 4 dx, that is equal to 1/4 is constant. You can pull it out. Integration of 1 is x. So 4 to 3, range is 4 to 3. Second fundamental theorem of calculus, you are going to get that is equal to this one. So that is quite simple, right? So that is just the uniform distribution. Another part, whenever you are working with uniform distribution, at that time, keep in mind this thing that your mean is the expected value of your random variable x. That is a plus b divided by 2, and sigma square variance is b minus a square divided by 12. And if somebody asks you how to prove this one, it's quite simple to prove. Theorem 6.1. Let me just stop sharing this one and let me show it to you how we can prove this one, because that is also the exercise problem 6.1 in your book. So I would say that exercise problem 6.1, or you can say theorem number, what is the theorem number? Theorem number 6.1. Yes, theorem 6.1. That it says that nu is equal to a plus b divided by 2, and my variance sigma square, that is given by b minus a square divided by 12. That is easy to prove, guys. If you want, I would say that fx is nothing but my fx, just by definition, rectangular distribution, that is equal to b minus a, if a is less than or equal to x is less than or equal to b. Okay, and this nu is nothing but this is I want to prove, right? This is what I want to prove. So I would say a part. So a part says that nu is nothing but the expected value of x, and expected value of x is nothing but integration a to b, and because of this x, I have one x over here into fx and dx, that is equal to integration a to b and x as it is, and fx is nothing but 1 over b minus a and dx. 1 over b minus a is constant, just pull it out, and here it is x into dx and a to b, and that is equal to 1 over b minus a, and integration is x square by 2, and here it is a to b, x square by 2 and a to b, and that is equal to, I can write that is equal to 1 over b minus a and 1 by 2, that I can pull it out, and this x square can be replaced. This x is replaced by upper limit and lower limit in between negative sign. Second fundamental theorem of calculus, so 1 by 2 and 1 over b minus a, and here is just simple factors a minus b and a plus b. This will get cancelled out, so I'm going to get a plus b divided by 2, and that's what we are looking for. Look at here. So just use your previous knowledge and try to prove the formula, something like this. It's not hard, and if somebody says that I want to prove b, okay, no problem, not the difficult task. So here it is says sigma square, and sigma square, that is given by, for sigma square, what was the definition? Short definition, ex square minus nu square. Already I have nu, so I can take the square of this one. But before that, I want this ex square. So let me use this ex square in right side. So ex square is nothing but integration of a to b. Because of this x square, I have x square over here, and fx is 1 over b minus a and dx. That is equal to 1 over b minus a constant. Integration of x square is x cubed by 3 and a to b. Oh, cubic is there. Okay, 1 over b minus a, and 1 by 3 is also outside, and b minus a cube. B cube minus a cube, sorry. B cube minus a cube. If you have b cube minus a cube, I would say that I can write that is equal to 1/3, and here it is, factor is b minus a, b square plus ab plus a square divided by b minus a, because factor of a cube minus b cube, or x cube minus y cube, is x minus y, x square plus xy plus y square, reverse sign. Okay, here and here. So this will get cancelled out, and I'm going to get that is equal to a square, or a square plus ab plus b square. A cube plus b cube is a minus b, a square plus ab plus b square, if I'm not wrong. Okay, so a square plus b square plus ab plus b square, and that is equal, if you plug that value over here, you're going to get that is equal to a square plus ab plus b square divided by 3 minus nu square. Nu is equal to a plus b whole cube divided by 2 cube is 8. whole cube. So 2 cube, that is equal to 8. LCM is naturally 12, and a plus b cube can be written as a cube plus b cube plus 3a square b plus 3ab square plus 3ab square. So that is equal to, I can write a square plus ab plus b square minus a cube minus b cube minus 3a square b minus 3ab square. 3a square b minus 3ab square. And here my LCM, if I take 12, then here you can get 3 multiplied by 4, that is equal to 12, and 8 twos are, sorry. Yes, so 3 multiplied by 4, and here it is, why here it is 8, okay, 2 cube, okay, fine. It is cube, it is square, right? I'm sorry, guys. So why 2 cube? I'm sorry. Let me just remove this part, eraser, little bit wrong. Okay, so now I can continue with this one. So nu square, nu is equal to a plus b by 2. So a plus b square divided by 2 square is 4. 2 square is, and that's why, so a, that is equal to a square plus 2ab plus b square divided by 12. And if you want to write 12 over here, that means you have to multiply this by 4 and this by 3. If you open this one, you are going to get that is equal, and just simplify this one, b square divided by 12. So that's how you can prove this one. So not a big deal. Okay, let me again save this one. Good. And let me clear this picture. So that's how you can prove the formula. Again, let me go back and let's go for the book. My book says that normal distribution. So uniform distribution is okay, mainly the normal distribution. Always keep this thing in mind, guys, that whenever we are working with the normal distribution, it's the most useful distribution in statistics. Very, very important. I would say that please try to go through this paragraph. This paragraph is extremely important. It will provide you almost all the information about the normal distribution. Normal distribution is a bell-shaped distribution. So you have a bell shape of bell for this distribution, where top of the bell, means the top of that distribution, top of the bell, and if you take the vertical line, that will give you a mean value. And the spreading of that bell, look at here, spreading of the bell, this sigma, that is nothing but your standard deviation. So this bell, this deviates from mean value up to here and here. So that's why it is called the normal distribution. It is distributed both sides normally. The most important continuous probability distribution in the entire field of statistics is the normal distribution. And graph is called the normal curve, and it's a bell-shaped curve, as I told you, which is approximately described many phenomena that occur in nature, industry, and research. For example, I can give you physical measurements in areas such as materiological experiments, rainfall studies, and the measurements of manufactured parts are often explained with a normal distribution. So please keep this thing in mind, that the examples like materiological experiments or rainfall studies or measurements of manufactured parts. This type of things, we are using the normal distribution. Okay. Also, errors in some scientific measurements can also be extremely well approximated by the normal distribution. Errors in some scientific experiments, because whenever you are performing some scientific experiment, at that time you will have some error, and that error can be approximated by the normal distribution. It provides a basis from which much of the theory of inductive statistics is founded. This is the base. All inductive big statistical criteria are being found using this one. Abraham de Mobius, he developed this one first time in 1733. Abraham de Mobius. De Mobius, he has lots of contribution in mathematics. De Mobius theorem, that is a plus ib to the power n, or x plus iy to the power n. He gave us the expansion of a complex number, nth power, just like the binomial theorem. So that is his another expansion. And then after, the formula was also developed by the Gauss, another mathematician Gauss, and that's why it is called the Gaussian distribution too. So de Mobius, he developed this one mathematical equation for the normal curve. It provided a basis from which, as I told you, the theory of the inductive statistics is founded. The normal distribution is often referred as a Gaussian distribution too, in the memory of Carl Friedrich Gauss, I think German mathematician. And that's why it is called the Gaussian distribution. And the continuous random variable x having a bell-shaped distribution, as I told you over here in the figure, is called the normal random variable. And hence we denote the values, the mathematical equations for the probability distribution of the normal variable depends on two parameters. One is mean, that is nu, and the standard deviation, that is sigma, or positive square root of the variance, the standard deviation. And hence we denote the value of the density function x that is given in terms of n, x, nu, and sigma. So mainly nu and sigma, that is important because the normal distribution based on only this one nu value, that is the mean, top of the curve, and your sigma. And nu, n, x, nu, sigma is equal to 1 over square root of 2 pi. Sigma is out of square root sign. Look at it here. And e to the power negative 1 over 2 sigma square x minus nu square. Again, guys, it is hard to calculate all these things for different values of x. So again, we are not going to use the formula, but we are going to use the table given to you on the back of the book. After your Poisson distribution, immediately I think the normal distribution is given to you. That is page number, I would say 735 and 736. The normal distribution is given to you. So please, again, you can keep these pages with you so that you can use the numbers or the table given to you, probability density function. You can use this one immediately whenever it is required. Okay. So here you can see, now we are going to see different types of distribution. My first distribution you can see over here, that is equal to, look at over here. So my mean value, two normal curves having the same standard deviation. You can see same standard deviation. That means the deviation from here to here, that is sigma 1, and deviation from here to here, that is sigma 2, and sigma 1, sigma 2, they are same. So same standard deviation from the mean, but different means. So here the example of same standard deviation, but different means. Then after I can give you another example in which we have you can see, this time we see that two curves are there, but my standard deviation over here, that is nu1 and nu2. That means my mean is same now. Nu1 and mean is same, but the standard deviation here, my standard deviation is much more lesser than the standard deviation over here. That means as your standard deviation is more, that means your graph is more flattened along your mean value, or you can say x-axis. Make sure that whenever this is the probability distribution, probability cannot be more than 1. So maximum probability is 1. That means this is nothing but the area. Because this is the area, that means this area under this curve must be equal to 1. So if your graph, your distribution deviates, or I would say that standard deviation or deviates more flattened, in that case, your peak is coming little bit nearer to your x-axis. And if you synchronize, if your standard deviation is getting smaller and smaller, that means the height is getting higher and higher until it gets the value or area 1. So always keep this thing in mind. In other words, I can put like this. Here we have two curves are centered at exactly at the same position, that is our nu, on the horizontal axis. But the curve with the larger standard deviation is lower and spreads out farther. I repeat, the curves with the largest standard deviation, like this, look at over here, here to here, largest standard deviation for sigma 2. Largest standard deviation is lower, look at here, it's lower and spreads out farther. Remember that the area of the probability curves must be equal to 1. This area must be equal to 1, as I told you. And therefore, the more variables the set of observations, the lower and wider the corresponding curve will be. I repeat, the more, therefore, the more variable the set of observations, more variable the set of observations, the lower and wider the corresponding curve will be. Okay, then after, let me give you one more situation in which you can see over here, my mean is different, my standard deviation, both are different. So mean is different, standard deviations are different. That is in this case, right? So you can see sigma 1, so this one is different, this one is different. Look at over here, but because this is more scattered, I mean, it's a more deviated, sigma 2, that's why it is peak is a little bit lower than this first graph. Okay, now just keep in mind this thing, that based on all this inspection and all these graphs and examination of the first and second deviation of my nx nu sigma, we list following properties. There are some properties, 5 properties are there. Please guys, keep this thing in mind. The mode, which is the point on the horizontal axis where the curve is maximum, occurs at x is equal to nu. As I told you, the curve is maximum at the value nu, means mean value. That is the maximum curve, then after it comes down. The curve is symmetric about the vertical axis through the mean value. It's symmetric. When you can see over here, whatever the values you have over here on this side, exactly same value you have here on this side. So curve is symmetric about the x-axis. The curve has its point of inflection. I will let you know what we mean by the point of inflection. Point of inflection, that is a rate of change of function. Rate of change of function, that is a derivative, and rate of change of displacement is the derivative, and rate of change of that is a velocity. Rate of change of displacement is the velocity, and rate of change of velocity is nothing but the acceleration kind of thing. Now, whenever your graph changes the behavior in terms of increasing and decreasing nature of the function, means you are equating first derivative to 0. But whenever your graph is concave up, you can see over here, or concave down, this my graph is concave from this point somewhere over here. Please try to look at my cursor. Here to here it is concave down, and then after this point, after these 2 points, my graph starting going concave up, and then after this point again it will concave down. Concave down means some dome like this, and concave up means ball like this. So please keep this thing in mind. So this is my concave somewhere up to here, that is concave down, then from here to concave up. So concave down, concave up, it's a combination like this, concave down and up, right? And so that's why it is mentioned over here. The curve has its point of inflection. Whenever your second derivative, if you equate your second derivative to 0, you're going to get that point of inflection, from which curve changes the behavior in terms of concavity. Means after that point of inflection, my function will, if it is concave down, after that point it will start going for concave up and vice versa. If my graph is concave up, then after the point of inflection, again it will start going for concave down like this. Okay, so x is equal to nu plus or minus sigma. This is nu and plus sigma. Nu and plus sigma is somewhere over here. That is my concave inflection point, and that is plus, and nu minus sigma, that is over here. That means it is both the sides, it's exactly on the same line, exactly on the same line over here like this, exactly on the same line. So nu minus sigma, so if you open this one, that x is equal to plus or minus, that means nu minus sigma lies, x lies between nu minus sigma, your x, this x value lies between this nu minus sigma means here to here, and nu plus sigma here to here. And it concave upward otherwise, as I told you. The normal curve approaches the horizontal axis asymptotically as we proceed in either direction away from the mean. Either direction away from the mean, this is the mean value, and away from the mean means like this, and this is the asymptotically. It just goes like this. It goes like this, asymptotically. Same here. And the total area under the curve, that is always equal to 1, as I told you. Total area under the curve is always 1. So once we talk about this distribution, that means naturally we have the mean and variance of this distribution to the mean and the variance of this distribution. The mean and the variance of the normal curve are nu and sigma square respectively. And the standard deviation is sigma, because positive square root of variance is always the standard deviation. We know this thing. And there is a proof over here. I don't want to go into this one, so let's skip that part. But I would like to give you some of the information at this stage. I would say that so many probability distributions that can be described by the normal curve once these nu and sigma square are known to us, are specified. In this chapter, we shall assume that two parameters, nu and sigma, they are provided to us, but that will not always be the case. In the later chapters, it may be we are going to see, we shall make statistical inference when nu and sigma are unknown. So here nu and sigma, that is known to us, but then after in the later part, we are going to see that nu and sigma, they are unknown. In that case, how to take care of the normal distribution. We will see that part. Okay, the normal distribution finds number of applications, enormous applications as a limiting distribution. And under certain conditions, what will happen that normal distribution provides a good continuous approximation to the binomial and the hypergeometric distribution. So normal distribution that gives the good approximation to the binomial and geometric distribution. See the value of this distribution. This is the continuous random distribution, and this continuous random distribution that gives the approximation to the discrete random distribution like binomial and the hypergeometric. So the connection is normal distribution that combines these continuous and the discrete binomial, distributions, distribution for the random variables. Okay, and one more thing, maybe in chapter 8, we are going to see that about the sampling distribution, and it turns out that the limiting distribution of the sample average is normal. So limiting distribution of the sample average is a normal, or you can say normal distribution. So limiting distribution of the sample average is normal. So that is the, you can say, the best part or value of this normal distribution. That is the value of the normal distribution. So I would like to go for now my next part. My next part is article 6.3, area under the normal curve. Area under the normal curve. I don't want to continue much. Once we are done with article 6.3, then I think, and with some examples, then after we will probably stop, and the next time we may continue the rest of the part of this one. Let's see. Okay, so the curve of any continuous probability distribution or the density function is constructed so that the area under the curve bounded by two ordinates x equal to x1 and x equal to x2 equals the probability that the random variable x assumes a value between x equal to x1 and x equal to x2. That means my random variable x, and if you are using the normal distribution nx nu sigma as my function, and my random variable x lies between x1 and x2. This is my x1, this is x2. So my new random variable x lies between these two, and this is my new value, mean value, right? This x1 could be over here, this x2 could be over here, somewhere over here, just in left side of new or right side of new, or some over here, some over here. It could be anyway. Good. And this is the definition: 1 over square root of 2 pi sigma out x1 to x2 e to the power 1 over 2 sigma square x minus nu square and dx. So that is a definition. But again, we are not going to use the definition. We will be using the tabular form given on the back of the book. I gave the page numbers too. Okay. And we don't want to, if somebody is interested, he or she can go through the complete explanation given to you over here. Main part over here that I would like to convey, that is nothing but the difficulty encountered in solving the integrals of normal density function necessitates the tabulation of normal curve are for quick reference. Means we are going to take the help of the tabular form. However, it would be a hopeless task to attempt to set up these separate tables for every conceivable value for nu and lambda. Agreed. Fortunately, we are able to transform all the observations. Now see here what will happen. That main part, there are many, I just would like to explain to you that there are many types of statistical software that can be used in calculating the areas under the normal curve, whatever the area, and we want to find this area under the normal curve, some specific area, not the full. Full is always one, you know this thing. The difficulty encountered in solving integrals of normal density functions necessitates the tabulation of the normal curve for quick reference. And however, and that's why it is not always possible to set up the separate tables for every conceivable values for nu and lambda. Fortunately, we are able to transform all the observations of any normal random variable x into a new set of observation, and that new set of observation that is called the normal standard normal distribution, that is called the normal random variable z. So normal random variable x, capital X, is to be converted in terms of capital Z. Here your new value could be anything, but when you convert this one to normal distribution to, I mean to say, random variable x lying between this x1 and x2, right? So if you convert that one in terms of z at that time, the benefit is always you will be having your new value 0. So it is very easy to count this thing. New value 0, and your variance is always 1. So new value equal to 0 and your sigma square is equal to 1. If you have your new value equal to 0, new value is equal to 0. So new is equal to 0. So it's simply x square. And sigma is 1. So negative 1 by 2 and x square dx like this. And sigma is equal to 1 over square root is kind of gamma function or something like that. That's fine. Let's just go for this one. So please keep this thing in mind that whenever you are going to solve the examples based on the normal distribution at that time, we are converting our random variable capital X in terms of the random variable, normal random variable, I would say, not the simple normal random variable capital Z, using the formula Z is equal to X minus nu divided by sigma. Because nu is known to us, sigma is known to us, x value will be provided to us, we can find z value. Again, the benefit for this one is always you are going to get, look at over here, I told you 1 over 2 by z1 to z2, because now your integration is e to the power negative z square by 2, because now nu equal to 0 and sigma is equal to 1 always. Nu equal to 0 and sigma equal to 1. See, nu equal to 0 and sigma equal to 1. So you are converting your n x nu sigma to nz01 using this definition. That's it. So always we'll be using this definition. Okay, so the distribution of a normal random variable with mean 0 and variance 1 is called the standard normal distribution. So once you convert from your normal distribution random variable x to normal random variable z, it is called this, and that distribution is called the standard normal distribution. That distribution is called the standard normal distribution. The original and the transformed distributions are given maybe in some examples. In 5 minutes we are going to see that thing. And since all the values of x falling between x1 and x2, as I told you, all the values, they are falling. Look at where, sorry, look at here, all the values of x, they are falling between x1 and x2. Have corresponding z values, because now you are converting this, because once you plug this x value over here, x1, once you plug this x value over here, that means that will be converted in terms of z values. So x1 and x2 are converting to corresponding z values between, then after we are going to say z1 and z2. And the area under x curve between the coordinates x1 and x1, this is my area under the x curves, I would say x curve is now the area under the z curve, because now it is converted in terms of z between the transformed coordinates z1 to z2. And that's why I took the range. I converted range from x1 to z1, right? x1 to z1. And that is the normal standard distribution. Table A3 we are going to use, that is the normal standard distribution. Now, let me give you some of the things over here. Look at over here, this x1 to x2, this new could be, this new mean could be anything, this sigma could be anything. But if you convert by that definition, this definition, z equal to x minus nu over sigma, if you convert, you are going to get this one, z1 to z2, my nu is 0 and sigma is 1. See, so your life would be really, really easy once you adopt this method. Okay. Now let's try to see some of the examples And these examples are quite interesting, quite useful. Once we are done with these examples, then after I think rest of the things we can do with the examples. Okay, so let's start with my first example, or 6.2. It says that given a standard normal distribution, find the area under the curve that lies to the right of z equal to 1.84. Right of z means this one. Look at over here. Right of z 1.84, and between z equal to negative 1.97 to 0.86. Negative 1.97 to 0.86. Right, guys? So, given a standard normal distribution, and we want to find the area between these two. Area between these two. I would like to draw this picture and let you know this thing using the tabular form. So probably that would be more useful to you. Once you know the table, then after in next example onwards, I'm not going to open the table. But right now, let me open the table, and table is given over here. As I told you, that is the normal curve 735. So let me start my tabular form. I'm going to draw this picture on my whiteboard, so don't worry about this. And let me go for the tabular form 735. Okay. Normal curve. Look at over here, 735. Okay, guys. So let me stop sharing this one and let me start my whiteboard. This example, as I told you, that let me draw the picture, and it says that example 6.2, example 6.2, picture is something like this. This is 0, 1.84, naturally 1.84 that lies on the right of 0. And the example is to the right of z equal to 1.84, right of. Right of. Okay, so we want to find the area, find the area to the right of z equal to 1.84. Okay, that is my right of, means this one. You have to draw the picture in the exam. So that's why I'm telling you that please be careful. Asymptotes, this is my new equal to 0. And it says that between negative 1.97. Now negative 1.97, naturally that is over here. Negative 1.97. And 0.86. 0.86, that is somewhere over here. 0.86. And in between. So we are looking for this one, we are looking for this one. Let me start with number A. This is, I would say, number A. This is number B. A and this is B. Okay, A says that to the right of this one. Okay, right of this one. Now, what is my Z value? Z value is this one, 1.84 is equal to, because it is greater than on the right side. So what I'm going to do, that is equal to 1 minus, because this is total probability is 1. Total probability is 1. 1 minus this one. So 1 minus Z value, that is equal to 1 minus Z value is 1.84, right? So let me just share my table with you. 1.84. How can you read the table? See, 1.84, that means just go look at here. It's a negative numbers, and then after 0 and the next page you have positive number. 1.84, that is somewhere over here. So 1.8, 1 after decimal, the first position up to that you can see on the vertical line, and then after you can see on the horizontal line. So 1.8 I can see over here, and 0.04 I can add from the horizontal line. So if I try to match this one, 1.84, 1, 2, 3, and here I have to stop. So 0.9671, that's the value, 0.967. That's how you can read this one, 1.8, and this is 0.04, so 1.84, 0.9671. So let me write it down, 0.9671. 0.9671. So 1 minus 0.9671, and that is equal to 0.0329. 0.0329. So that is this area. That is this area. So what I did, I just tried to figure it out. This area, full area is 1, and it says that to the right of this one, right? And then after I subtracted this area, so this one is the area. Out of 1, I subtracted this one. This is the full area 1. Out of 1, I subtracted because Z distribution always starts with 0. So you are going to get this type of region over here. So this one is subtracted. So out of 1 full part, that means only this part is left out. That is the value. Same here. Now suppose Z value is negative 1.97 and 0.86. Right? So 1.97 and 86, that means I can write something like this. 0.86, right? So first of all, let me just let you know, stop sharing this thing, and book value 0. First of all, I would like to go for the right side, 0.86. 0.8 is over here. 0.86 is somewhere over here. 0.8051. So 8051, I'm going to take this value, 8051, 0.8051. And then after another value is negative 1.97, negative 1, that is on the previous page, negative 1.97, negative 1.9, negative 1.9, and here it is 7, negative 1.9 and 7, so 0.0244. 0.0244. That's how this is the way you can see the table. If you plug this value over here, so for this one I'm going to get, this is nothing but 0.8051 as I told you, and 0.0244, and that is equal to 0.7807. So this is the area, 0.7807, like this, 7807. My next, this is example, this one, example 6.3 says that suppose you have one normal distribution, something like this, and here is the mean value nu equal to 0, and you have k value, that probability of z greater than k is equal to 0.3015. 0.3015 is value is provided to 1. So this k value, we need to find that which line will be there for this k, and this area is given to you. This area is nothing but 0.3015. So we are going to find this. We are going to look at, now you have to be a little bit careful that which type of value is provided to us. And another example is, this is says that p greater than k, and another example that is for p, probability of k is less than z is less than negative 0.18, and that is equal to 0.4197. 4197, and here it is something like this. This is my mean value 0, and my k value, z value, lies between, k is somewhere over here, and because it is less than and negative 0.18, negative 0.18, I would like to say something like this. So this is the region I'm looking for. This is my mean value. This is the region I'm looking for. Okay, so let me first take care of this part. Now, whenever you have this type of things at that time, please keep this thing in mind that 0.3015 that is given to you, right? 0.3015. Okay. So as I told you that normal, always we are looking from here to here. In that case also here to here. So that means here to here. Total area is 1. Total area is 1. So I am going to subtract 1 minus 0.3015. 1 minus 0.3015, that will provide you how much? I think approximately 0.698555 10 and 9 and 9. Yeah, 6985. Now you have to take care of this 6985 in a tabular form. In a tabular form, I'm going to say that, look at here, the table. 0.6, you need to find, because of probability is provided to you, you need to find that 0.6985 somewhere over here in these numbers. You may not get exactly the same number. Sometimes numbers are same, sometimes they are very close. So you have to consider that close numbers. So let me go over here because I'm looking for 0.6985. 6985 is somewhere over here, 0.6985 somewhere over here, right? So I'm going to get 0.6985, 6985, So 0.69 here. So I can say 6985. See, I'm getting exact number this time. That's fine, but it may be suppose 0.6984. Then you don't have that number over here, right? So in that case, we are going to consider this part. If you are given suppose 0.698384, so that number you cannot see on this table. So at that time, we are going to consider this part. So here it is 0.5 and 0.2 0.52. So my K value is 0.52. Like this. So my K value is 0.52. Okay. Same here. K value is 0.52. So my K is equal to 0.52. So if you draw the K value like this K over here, 0.52, in that case, you will be having this area, this one, and the area is this one. Now my K value lies over here. This is my K, and I'm going to find my K value over here too. Again, the same kind of things. Look at over here, guys. First of all, I'm going to find negative 0.18, right? Negative 0.18, and that is equal to, where can I find this one? Because now Z value is given for this one. This is okay. This is okay. We don't have any problem with this one. So we are going to find this one first, and then we are going to, because Z is less than 0.018, negative 0.018. This is your negative 0.18, this one, negative 0.18, negative 0.18. So what I'm going to do, that is negative 0.8, that is starting from, don't forget, don't consider this K. Right now, I would say that, let me show it to you. I'm counting here to here. And this is my negative 0.18 given to you, right? Z value. So this area is nothing but, that's what I'm going to count. This area is something using the table, right? Using the table. And then after I'm going to subtract that area. Then after, I think, yes, 0.18 is this one. And I can write that is in the form of equal to this one. And we see that area between K and negative 0.18. Okay. That we are going to find something like this. Okay, let me find like this. I want to find my K. So first of all, the area over here, stop this one and go for the table. Go for the table. Negative 0.18. Negative 0.1 is over here, and 8 is, there is 8, number 8 is second last. Okay. So negative 0.18 is somewhere over here, 0.4286. 0.4286, right? 0.4286. That is the total area to the left of 0.18. Okay, and we see that the area between K, you are given one area. Okay, that's what I was thinking. Why I'm getting, okay. And now, so this one is, let me write it down, this number. 0.4286. I got you. 0.4286. So 0.4286. This area is 0.4286. 0.4286. And you are given the area, this one. Look at over here. The area between this to this, area between this K to this one, this area is given to you that is equal to this one. So naturally, I can find this area because this whole area is this one. This area is given to you. So you can find this one and that is your K value. So my K value will be 0. What I figured it out, 0.4286 for this one. 4286 from this one and minus 0.4197, that is the area I am given between this and this, between this and this. So it is something like this one minus this one. So I'm getting my K value. So here, so that is my K value is equal to 0. Here to here minus here to here, because it is on the left side. So please keep this in mind. It has to be negative. So negative 2.37 because it's on the left of the mean. So please keep this thing in mind. Negative 2.37. Actually, it is, that is equal, let me give you exact answer. So 4286, that is equal to 0.0089. Once you have this 0.0089, again go to the table. If you go to the table, you're going to get, look at here, guys, 0.0089 you need to find. 0.0089 you will find somewhere over here. Look at here. No, somewhere here. negative 2.3. And then I want negative 2.3. Negative 2.3 and 00, what we want, 0089. Do we have 0089 over here somewhere here, guys? 0089, 0089 here, see, 0.0089. So I would say that it is nothing but negative 2.37. So my K value is negative 2.37. My K value . So my K value, so that is equal to this one, and hence actually this is not K because K is nothing but this probability. So K value is equal to negative 2.37. So that's how you can do. I repeat that suppose you had this type of graph and you were given probability. This is my mean value. I did not see this value and that's why, but now it is okay. This is my 0. And this is the value. Let me change the color. This is the value I am given, that is equal to negative 0.18. And here it is my K. In between, whatever the area, that area is provided to us, and that area is nothing but 0.4197. 4197. This is okay, but this is from here to here. 0.4197. This area is given to you, 0.4197. We first use negative 0.18 and try to figure it out, the area starting from here to here. And that area is given by from here to here. Let me change the color, guys. That area is given by now, that is the area, this whole part. The whole part area, look at my color, please. Whole area that is given to you, I mean to say that is not given, but that what we found, that is 0.4286. If you subtract this one, because whole part minus this part, so 0.4286 minus 0.4197 means you're going to get 0.0089. Then go to table A3, right? That is for normal distribution. Yes, table A3, find that some numbers are there, go for that number and try to go from left hand, this side and this side, and try to make the number. You're going to get K is equal to negative 2.37. So that's how we find the values. Let me just save this one. Okay, and let me clear the drawing. The rest of the things, I think, guys, that is simple. Let me go for now one more example. Now I will not go for, you know, that table, because now you know how to look at the table, how to see the table. Suppose I have another distribution, normal distribution. normal distribution. And it says that given the random variable x having the normal distribution with nu equal to 50. So we are given that nu is equal to 50 and we are given sigma is equal to 10. Now nu is not 0. It's now different than the previous two examples. Find the probability of that x assumes a value between 45 and 62. Find the probability. Find the probability that x assumes a value or takes a value, assumes a value between 45 and 62. 45 and 62. That's fine. Now I would like to first convert my x value in terms of the z value. So let me use my z value first. So I would say z1 is equal to x minus nu divided by sigma. X minus nu. Instead of x, I would like to write x1 because I have two x values. And my z2 is equal to x2 minus nu divided by sigma. X1 is nothing but, yes, please, 45. This is my x1 and this is my x2. X1 and x2. 45 nu is equal to 50, sigma is equal to 10. Here it is 62 minus 50 divided by 10. Here I'm going to get that is equal to 1.2 and here I'm going to get that is equal to negative 0.5. So my z value, if I want to convert my, actually I'm given like this, the given thing, given is something like this. My nu value, nu equal to 50 and this sigma is equal to 10. That's what given to us. And my x values were 45. Let me use another color, may be helpful to you. Sorry, 45, that is because it is 50, so 45 is here. 45 and 62. So this is my 62, x is equal to, and x equal to 45. So we are asked to find this region. And we are converting this one in terms of z distribution. This is my x random variable. Look at here, x random variable. We are converting that one to z. That I have converted z1 is equal to negative 0.05 and 1.2. This is 0, nu equal to 0. Negative 0.5, that is somewhere over here, very close, right? Now z1 is equal to negative 0.5 and z2 is equal to 1.2. Z2 equal to 1.2. So I have converted my x random variable to z random variable. So z normal standard distribution we are looking for. Once I have this one, that means now I can start my example. I can start the example that therefore probability of 45 is less than x is less than 62 is equivalent to say that probability of negative 0.5 is less than z is less than 1.2. Is less than 1.2. This can be written as probability of z less than 1.2 and minus probability of z less than 0.5. Always, you know this thing from the previous chapter, right? You can use the table over here. You can use the table over here. Here you're going to get that is equal to 0.8849 and 0.3085. And that is equal to your answer. So 0.5764. That is the answer. That is the answer. I would like to go for one more example. And this is example number 6.4. Example 6.4. And now let me go for example number 6.5. Example 6.5. Example 6.5 says that given that x has a normal distribution with nu equal to 300 and sigma is equal to 50. Find the probability that x assumes a value greater than 362. So x assumes the value 362 and we want to find the probability. What is the probability? So again, this is not 0. So first of all, we are going to convert this one in terms of z Z distribution because Z normal distribution, or standard normal distribution because your nu has to be equal to 0 for that one. So let me use Z is equal to X minus nu divided by sigma formula again. My X value, that is 362 minus nu equal to 300 divided by sigma equal to 50, and that is equal to naturally 1.24. See, that values are reduced is like anything by very small. So probability of X greater than 362 is equal to probability of Z greater than 1.24, and that is equal to 1 minus probability of Z is less than 1.24. If you use this one 1.2 and then 4, you're going to get one value, and that value is 0.8925. I have table with me, and if you subtract this one, you're going to get 0.1075. So that's how you can get the answer. This is the answer. So it's now very easy. And if you want to look at this one in terms of your given thing was something like this. The given thing was like this. This was my 300 nu equal to 300, and this was 362, and greater than means this one. So that probability is, this probability is nothing but 0.1075. 1075. Now sometimes what happens that very small portion is left out. Just look at here, guys, and then after, I think we need to stop. I don't want to start article 6.4. 6.4 is just the applications, how we can use the same thing in terms of practical examples. But I think I would like to divide this thing into two parts. So we are going to refer 6.4, sorry, and the examples next time. So let me just go through the normal curve in a reverse way. So normal curve in a reverse way, that is something like this. Let me save this file too. And let me clear the picture. So now I would say that normal curve in a reverse way. So using normal curve in reverse way. Using normal curve in reverse. Normal curve in reverse. Right? In reverse, I mean to say that okay, let me explain to you something like this. Sometimes we require to find the value of Z corresponding to the specific probability that falls between the values in the listed table. So value of Z, that means suppose we are given some Z value and we are looking for X values. In all previous examples, the X random variable X values were provided to us and we found Z value. But in a reverse way, sometimes we are looking for X values and the Z value is provided to us. Then how can this formula will work? So naturally my Z is equal to X minus nu over sigma. So this implies that sigma times Z is equal to X minus nu. So this implies that X is equal to nu plus sigma C or Z sigma. X is equal to nu plus Z sigma. In your book, it is mentioned nu plus sigma Z or Z sigma, whatever you want to say. I think sigma Z, this is the right form. X is equal to nu plus sigma Z. And I can give you one of the examples. Whenever you are given in terms of some percentage, it's just the layman idea, just some percentage at that time, just keep this in mind, keep this one in mind, that you are given the area in terms of Z and you are looking for X. Like this one, suppose my example 6.6 says that given the normal distribution with nu is equal to 40 and sigma is equal to 6. Find the value of X, that A part, 45% of the total, 45% of the area to the left, 45% of the area to the left, and the B part is 14% of the area to the right, 45% of the area to the right. So what will happen? What will happen over here? 45%. Let me just draw two pictures. For A part, I would like to draw one picture over here. And it says that 40%. So my nu is equal to 40. This is my nu. And 45% means 45% that is equal to 0.45. So this area, this is 40 and 45%. This is not exactly, this is actually, this is 50%, this is 50%, but it says 45%. So I would say that this area. So that is nothing but 0.45. This is nothing but 0.45, or I would say 0.45, this part. .45, and that this was nu is equal to 40. Nu is equal to 40, right? And my sigma is equal to 6 given to us. Sigma equal to 6 given to us. And this is my figure A, and my second figure says that 14%. This is area to the left, and this is right. This is my nu is equal to 40, sigma equal to 6, and here it is. This is nothing but 0.6. Oh, sorry, if 14% means 0.14. 0.14. Yeah, 0.14, right, guys? So what will happen over here? See, if I want to solve the first one, I can write something like this. Area 0.45 to the left of the desired X value over here on the shaded region, we require Z value to the Z value that leaves an area 0.45 to the left, right? 0.45 to the left. Whatever 0.45 you have in your tabular form, you need to figure it out according, because this is the area provided to you, 0.45. Let me go back and try to figure it out, my 0.45. Let me stop this one. Again, I think I need to show you the screen. I mean to say table. So 0.45. Where can you find 0.45? Just look at here. Yes, you need to find that one because that's the area is given to you, probability. So 0. If I say 45 somewhere over here, look at here. So I can say 0.1, no, 0.1, 45 is somewhere over here. See, 4522, that is 3, 1, 2, and 3. 0, 1, 2, and 3. Right, 4483 and 4522. This is a little bit far. 4483. This is the closest number. This is the closest number amongst the full table. So that's why I would say negative 0.1 and 0.123. One negative 0.13. So my Z value is negative 0.13. That's how you can figure it out. Now my Z value is negative 0.13. So let me write this value here. Z value is negative 0.13. So I can say that my probability of Z value is negative 1. No, I think it was 0.13, right? Probability of Z value less than negative 0.13 0.13, and that was equal to 0.45. That's the meaning, right? So naturally I can find my x is equal to, as you know, that nu plus sigma, nu plus z sigma, you can say, or sigma z, nu plus sigma z. Nu is known to us, that is equal to 6, sorry, nu is equal to 40 plus sigma is equal to 6, and this I figure it out, negative 0.13. Use your calculator and you are getting 39.22. That is my x value. That is my x value. Exactly same way I can find the second part, right? Exactly same way I can find my second part. Okay, so same way I mean to say that it says that this is left and this is right, right to 0.14. So first of all, what I need to do, we shaded the area here equal to 0.14 to write of the desired X value. And this time we require the Z value that leaves 0.14 because this one minus this one. Okay, so 0.14 is this one. So naturally 0.14 is this one. So this one is nothing but 0.86. So this one is 0.86, right? If you go to the table and try to figure it out, what is 0.86? So again, let me go back to the table. Let me go back to table and try to fix my 0.86. 0.86, I'm going to get, not here, 0.86, you're going to get something, 0.1118, somewhere over here, 0.86, 82, 85, 86, and look at here, 85.99 and 86. That means I'm going to go at 1.0 and 8. So 1.0 because this is the closest value. 1.0 and 8. So let me consider this value. 1.0 and 8. So let me close this one. Let me again go back to my whiteboard and I'm going to get, that is the part A is done. And now part B. So 14%, 0.14 on right implies 0.86 on left. And this 0.86 corresponds to 1.08, and that is my Z value. And therefore my X value is equal to nu plus sigma Z. Nu remains the same, that is equal to 40 plus sigma is 6, and Z is equal to 1.08, and whatever the value we are getting, maybe 46.48, that is nothing but my X value. So that's how you can go for the reverse way. We are going to solve the example next time. Let me save this file. And almost everything is done. Same thing we are going to use in our practical purpose. Which type of practical examples are being used? I mean, which type of practical examples are solved using or by taking the help of this normal distribution, X values, Z values, how to convert them, all these things that we are going to see next time. But that's just, I would say, kind of repetition or kind of revision. The main part of these articles, both of this article is done. So let me just stop sharing this part too. And I think, yeah, this one is done. And I'll see you next time, guys. Thank you so much.